So before we launch into the lecture, just a few reminders real quick. Today's Wednesday, which means we're a week out from our first test. Our first test is going to be next Wednesday in lecture. We're going to take the entire time to do the test, so you have an hour and 50 minutes to work on it, okay? I hope that you've started studying already. That means going through the review problems and starting to prepare your cheat sheet. So remember, on the day of the test, you get to bring a half sheet of paper. It's filled out on the front and back, and you can put whatever you want on that piece of paper that you think may help you come to test. Okay? You also can have a calculator. The schedule in the upcoming weeks is a little bit strange. So on Friday, we have the President's Day holiday of this week. So Friday of this week, we have off. So if you're in lab on Friday, normally we're not going to be meeting this Friday for lab. And Monday of next week also, we have the day off. So no lecture, no lab next Monday. Okay? So the only thing going on in the lecture portion of class next week is the test. Okay? That's all that's really happening. But if you're in Wednesday or Friday lab, you'll be meeting for lab next week. Okay? So to summarize, Friday is a holiday of this week. Monday of next week is a holiday as well. Okay? Any questions? All right, with that said, we're going to jump into a new chapter. This is the chapter on capacitance, which in the textbook is covered in Volume 2, Chapter 8. Now, this is not material that's going to appear on the upcoming test, okay? But we have to make some headway, make some progress into this new material. So after the test, we'll resume this lecture and dive deeper into the topic, but just be aware, this stuff is not going to appear on the test, okay? So let's start by defining this term called capacitance. What does it mean? How is it calculated? And why is it relevant in the context of electrical circuits in particular? Okay, so there's a device that I'm going to introduce you to here, if you haven't seen this already, called a capacitor. And a capacitor is simply a device that stores electric charge. And the simplest model of a capacitor is this. You have two conductors, and each one of those conductors holds some amount of charge. And the charges on those two conductors is equal and opposite. So quite literally, if I have a positive Q here on some conductor and a negative Q here on some other conductor, that constitutes a capacitor. That's your basic configuration. But there are more than, there's more than one way to build a capacitor, right? We can do it, let's say, like this, where the two different conductors are these big sheets of metal, which then we wind up into a tight space so we can pack it efficiently into a small volume. Now, here are some of the common uses for capacitors, by the way. So, for one, they're really good at storing charge, okay? And if we have some device where we might want to access that charge later, for example, the flash unit in a camera, or let's say a backup power source in a computer, that would be a good use of a capacitor. Capacitors can also be used for memory in a computer. So, for example, we could have the 0 as a binary digit represented by a capacitor that's charged, and a 1 represented by a capacitor that is uncharged, right? That could be used for storage of memory. We also have variable capacitors. So the capacitance, which I'll define for you in a second, is something we can change in these devices. And you can use that for radio tuners or computer keyboards. For example, let's say there's a capacitor right underneath one of the keys on your keyboard. So if we press it down, we essentially change the capacitance of this thing, and that can be used to register a keystroke. Okay? So this is just a list of some of the different uses for this sort of device. There are a lot more we can think of, but hopefully this gets you thinking about the idea. Okay. So now we're going to move on to something called a parallel plate capacitor. And a parallel plate capacitor is basically the simplest design for a capacitor that we can think of. And we're going to be using this quite a bit, although there are other designs, as we'll see. So basically, it's exactly what it sounds like. We have two parallel plates. So we have two flat metal plates, and they're separated by some distance. Now, in order for this to work in the way we want it to work, the distance that we separate the two plates by is pretty small compared to the actual size of those plates, right? So let's say I have square plates like this, right? What we're saying is the length of the plate on either side is very, very large compared to the separation between the two plates. So this is what it would look like if we were looking at it from the side, where we're just looking at the plates edge on. They're separated by some distance we'll call d. And as I said before, there's going to be equal yet opposite charges on those plates. So plus q minus q. So from here on out, if we just simply say q, we're referring to the magnitude of the charge that's on both plates. But it's understood, right, that one of them has positive q and the other has negative q. Okay? So it's just a shorthand way of saying what that charge is. Okay. What also comes into play, as we'll see in our equations, is the area of each plate. So that's just the surface area of whatever this metal sheet is. Doesn't have to be square, by the way. It could be circular, but it has some sort of area to it. Okay, last thing to say about this. In the simplest model of a capacitor, we just imagine that there's completely empty space in between the plates. So that's called a vacuum capacitor, by the way. But what we'll actually do to make our capacitors perform better in the real world is typically fill that space with some sort of material. And we call that material a dielectric. And that's going to be something we'll cover later on in this chapter. Okay? So we can have it filled with vacuum or with some insulating material, which we're going to refer to as a dielectric. All right. So any questions so far? So now let's talk about the simplest circuit we could possibly put a capacitor in, which is to connect our capacitor up with a battery. Okay? Now, a battery is something that we're going to look into in more detail in the next chapter, and we'll see how a battery actually works and what kind of chemical reactions are happening inside of a battery that makes it work. But for now, we just want the picture of a battery as a voltage source. Okay, so for our purposes right now, a battery is just a voltage source, meaning there is a constant potential difference, aka voltage, between its two terminals. Right? So if I have a 1 volt battery, it maintains a 1 volt potential difference between the positive and negative terminals. If I have a 9 volt battery, then it's 9 volts, right? Okay, so here is a picture of our capacitor, which in diagrams like this, we show with these two parallel plates. And then here is a battery, which in diagrams we show like this. The negative terminal is a small line, and the positive terminal is a longer line like this. Okay? And then we connect them with some wires like this. Okay, so what happens when we take our capacitor, which is initially not charged up at all, so there's no charge on either plate, and we connect it to this battery? Well, it's pretty straightforward. Electrons are going to want to come off of the negative terminal of the battery, and so whichever plate of my capacitor is connected to the negative terminal of the battery, that's going to acquire a negative charge. So we have minus Q right there. And then the other plate, since electrons are flowing in this circuit like counterclockwise, right? Because electrons are flowing away from this plate, it's going to acquire a positive charge. So when you connect a battery to a capacitor, its plates become charged with plus Q and minus Q as the charge. Then the question becomes, well, how much charge is there actually accumulating on the plates? What is the value of Q in any given situation? That's what we want to know. So it turns out, experimentally, the magnitude of the charge that accumulates on those plates is just proportional to the voltage you apply, which should be fairly intuitive, right? The higher the voltage we apply to the plates, the more charge we're going to get accumulating on those plates. And it's a direct proportionality. So what we say is Q is directly proportional to V, where V is this voltage we apply. So whenever we have a direct proportionality between two variables, we can say there's some kind of constant of proportionality involved in that, okay? So I'm going to write this in a slightly different way. Q is equal to C times V. Now C is just some kind of constant of proportionality here. Okay, well, it turns out the name of this constant C is the capacitance, and it has to do with our capacitor and how much charge it's actually capable of storing. Okay? So we all good on this? Charge is proportional to voltage. The constant of proportionality is called your capacitance. Make sense? Okay, so let's get into the capacitance now. I'm showing you a graph here where on the vertical axis we have the magnitude of the charge that accumulates on the capacitor plate. So that's Q. And on the horizontal axis we have the applied voltage, which is V. And since we said there's a direct proportionality between these quantities, we expect that if I were to graph this relationship out, it would be a straight line. Okay? However, you're going to get a line with a different slope depending on which capacitor you use. So let's say this is capacitor 1, right? It has a very large slope. So that means it's accumulating a lot of charge for a given amount of voltage compared to these other ones. If I look at capacitor 3, it has a very small slope on this graph, and that means it's accumulating a lot less charge for the same amount of voltage compared to this one. So what that just means is this one has the biggest capacitance, this one has the smallest capacitance, and this one is somewhere in the middle. So if we were to rank these, we'd say C1 is bigger than C2, is bigger than C3. Does that make sense? So it's just about how much charge these are capable of storing as a function of voltage. Okay. So let's get into how capacitance is measured and how we can calculate capacitance given a certain geometry for our capacitor. All right, so if we were to define this in words and not just with the equation, we could say that capacitance is the measure of our device's ability to store charge. Okay, so in other words, if the capacitance is larger, it has a better ability to store charge than other devices. And the way we define it, as I said, is with the equation Q equals C times V. But if I rearrange that, I could say C equals Q divided by V. So this is a little bit more suggestive to see what capacitance really means, right? Because if C is equal to Q divided by V, well, Q is just the magnitude of the charge accumulating on each plate, and V is the magnitude of the voltage or potential difference between the plates. So it's how much charge you get per unit of voltage accumulating on the plates. That's how you want to think about this. So let me ask you this. Q, that's an amount of charge. What is our unit in the SI system for electric charge? That's the Coulomb, right? And then voltage is measured in volts, right? Pretty straightforward. So our unit for capacitance is some kind of unit of charge divided by some kind of unit of voltage, which is a Coulomb per volt in the SI system, right? So we have a special name for this unit of a Coulomb per volt. It's called a farad. And we use capital F to denote a farad. So if you have a capacitor, its capacitance is measured in farads. And oftentimes you'll see it in microfarads or nanofarads or things like that. Okay, so how do we look at a certain capacitor and figure out what its capacitance actually is? There's a process we can go through to calculate this. And we're going to see a few examples of it. But it basically goes like this. Number one, first, we have these two conductors, right? And they're charged to plus Q and minus Q. So that means in between the two conductors, there's going to be an electric field. Like imagine the parallel plate case, right? We've already seen in lab and in other places how there's an electric field when you charge up two plates with equal but opposite charges, right? So we have a way of calculating that E field. We know how to calculate E fields with different methods, right? Then the second thing is we're going to calculate the potential difference. That is the voltage between our two conductors, because we learned about how to do that in the last chapter. Delta V is equal to minus the integral of E dot dl. Okay, so I figured out the E field. I use that, I integrate over that to figure out the voltage. And then the last step is pretty simple, right? Basically, delta V is something we calculated step 2. If I just plug that in to the definition of capacitance, where C equals Q over V, just plug in your voltage right here, you get out a formula for the capacitance, okay? And as we're going to see, what that formula looks like depends on exactly how you design your capacitor. So if we have a parallel plate capacitor, we arrive at a certain formula. If we have a cylindrical capacitor, we arrive at a different formula, and so on. So is this clear what we're doing here? So we're gonna go through a couple examples like this in just a minute. So the first example is the parallel plate capacitor. What I'm going to show you is how we come up with a formula for the capacitance of this type of capacitor. So let's go through it real quick. Here are my two parallel plates, okay? I have a positively charged plate on the left side, and then I have a negatively charged plate on the right side in this picture. And we could talk about the kind of charge that's accumulating on these plates in a few different ways. We could say, I just have a total charge of plus Q over here and a total charge of minus Q over here. Or I could talk about this variable sigma. So anyone out there want to remind me what sigma means?
Surface charge density?
Yeah, surface charge density. So that would be the charge per unit area on each one of the plates. So let's just use that for what follows. So we have the charge per unit area. Okay, in the very first lecture that we did, I hope you remember this, we showed that the electric field near a large plate of charge is basically uniform, and the magnitude is given by E equals sigma over 2 epsilon naught. So do you remember when we derived this? If you have a big plate of charge, that's the E field it creates nearby. Yeah?
In the middle, is it just surface charge density over epsilon naught without the...
Yep, so that's what we're going to see once we go through the exercise a little bit, yeah. So notice I have 3 points labeled here, right? Let's start with point number 1. My question for you is, we're going to have two E fields to add together, right? We have the E field from the positive plate and the E field from the negative plate to get the overall E field in the center. So for the positive plate, at point 1, what direction is the E field pointing in?
Right.
Yeah, it should be pointing away from this positively charged plate, so it's pointing to the right at point 1. What about for the negative plate?
When is it going towards the south? Wait, no.
Okay, so if we're right here, we're going to have an E field also pointing to the right, because it's going towards the negative plate. Remember, E fields go away from positive charges towards negative charges. So when we add the two E fields from the two plates, when we're in the middle of the two plates at point 1, E positive and E negative both go in the same direction. Okay? That makes sense? Okay, what if we're at point 2? Well, E positive would be going to the right, away from the positive plate, but E negative would be going to the left, towards the negative plate. And you can see that we would get some sort of cancellation here. And the same goes for point 3. So the E field would be pointing away from the positive plate and then towards the negative plate. So we're getting cancellation both on the right side and on the left side. So in other words, if we're outside of the plates, if we're not in between the plates, we get cancellation of the E fields more or less. And if we're right in between the plates, the two E fields reinforce each other. So if each one is given by this formula, this is your question, right? If each one is given by sigma over 2 epsilon naught, if I add two of those fields together, then I get just sigma over epsilon naught. So the E field between the plates is sigma over epsilon naught. I actually need to know this for what comes next, because guess what? We're going to take the voltage between the two plates as our next step. So we know the E field. Now we're going to find the voltage between the two plates. Make sense? All right, let me know if you have any questions, but we're going to keep going with this. So by the way, In one of the previous labs, you mapped out what the E field between two capacitor plates looks like. And if you recall, it's something like this, where right in the middle, the lines are pretty much going straight from positive to negative, but then towards the edges, it bends a little bit. So what we're going to do to calculate the voltage between the plates is just integrate over this E field from one plate to the other. So remember, whenever we calculate potential difference, it's given by this integral. Delta V equals minus integral E dot dl, where dl is the displacement along a path from some starting point to some ending point. So if I want to know the voltage between the two plates, well, I better start my integral at one plate and then end it at the other plate. So let's go from the positive to the negative plate. That's an easy way to visualize this. So you see my path I'm taking as I integrate starts here at the positive plate, and then it ends here at the negative plate. That's the path we're going to integrate over. So here's how that works. We have a dot product, E dot dl. Any dot product can be expressed this way. It's the magnitude of the first vector, which is E, times the magnitude of the second vector, which is dl. And in this case, I hope you see that the angle between those vectors is 0, because the direction we're moving in, going from the positive to the negative plate, is exactly the same as the direction of our E field. So that's just cosine of 0 right there. The other thing we should notice is that the E field, the magnitude of it, is going to be uniform as we go from one plate to the other. So we can pull this out of the integral. You pull the magnitude of E out of the integral. And then we just have integral of dl. Now, let's be clear on what this means. We're simply adding up all of the tiny little displacements that we take going from one plate to the other. So that's just going to be the total distance between the plates at the end of the day, right? Which we're calling d, okay? So this is minus the magnitude of the E field times d. So it turns out you drop in potential as you go from positive to negative, okay? But we have magnitude of the E field times d. All right? So we figured out what the magnitude of the E field between the plates is, haven't we? We just did that. So why don't I insert that expression for E right here, okay? So you see what I did? In place of E, we're going to write sigma over epsilon naught. So we have minus sigma over epsilon naught times d. That's the voltage between the two plates. Okay. So if we're just interested in the magnitude of the voltage between the two plates, and that's the case, we don't care about the sign when we apply the definition of capacitance. We just want to know the magnitude of the voltage. I'm just going to get rid of that negative sign, okay? So just think absolute value here. So we have sigma d over epsilon naught. Okay. Now can someone tell me what's the definition of sigma? What's an equation I can use to replace that variable?
Q over A.
It's just Q divided by A. It's the charge per unit area. So I can write this as Q divided by A. And when I do that, notice what happens. The magnitude of the voltage between the plates is now Q times D on top, and then A times epsilon naught on the bottom. That's what we have for the voltage between the two plates. Make sense? So the last step is pretty simple, right? The definition of capacitance for this device here is Q, which is how much charge is on the plates, divided by V, which is the voltage between the two plates. And of course, with both Q and V, we're talking about absolute values, okay? So what happens if I take Q divided by V? What do I get? Take this thing and put it downstairs right here. What do we get?
A epsilon naught over D.
Yeah, so the Q's will cancel out. You see that? And I just get A times epsilon naught divided by D. So this is the formula for the capacitance of a parallel plate capacitor. Notice it just depends on basically two things. the area of the plates. So the bigger the area, the more the capacitance will be, and the distance. Okay, it's inversely proportional to the distance. Epsilon naught, by the way, is just a constant. So the only features of the plates that matter are area and distance. That's pure geometric factors, right? Just how big do you make the plates and how far do you space them out? That's the only thing that matters. What we'll see is if we put some material in between the plates and not just empty space, it slightly changes this formula, but not by much. So we'll get to that in due time. All right, so any questions on how we did this one before we move on? All right, so that's a big result. Let's put it in a box. C equals A epsilon naught over D. That's for a parallel plate capacitor. Okay, let's do an example real quick. We have a parallel plate capacitor here. It consists of two circular plates of radius 75 centimeters, and they're separated by a distance of 0.125 millimeters. And we're assuming that there's just empty space in between the two plates. So first question is, what is the capacitance? Then two follow-up questions. Let's say we connect this capacitor to a 12-volt battery. How much charge will accumulate on the plates? And then second follow-up, what if we use a 48-volt battery instead? Go ahead.
Yeah, I know this probably isn't all completely relevant, but I'm just curious, like in the batteries, is it actually like empty space, or is there actually like still air in there, or is the air just negligible?
In the battery?
Yeah, like do they actually manage to make it like a vacuum, like true empty?
Okay, so there's a much different set of things going on inside of the battery, which we'll get to in the next lecture. Yeah, but in a capacitor, so yeah, the real world, usually it's going to be filled with some material. And again, we're going to build up to how to deal with that, but it really doesn't modify the equation that much. To kind of spoil it, you just increase the capacitance by some numerical factor. You just multiply it by some constant thing. So it doesn't really change the equation that much. Okay. So let's do this one. Capacitance. We have a parallel plate capacitor, so we're going to use C equals epsilon naught times A divided by D to get the capacitance. All right, so does anyone remember the value of epsilon naught? 8.85, 10 to the minus 12. And we have some crazy units attached to that, but what I want to show you real quick is that the units can be expressed as farads per meter. Okay? I'll show you in a second where that came from. But let's just write the rest of the numbers out. The area is going to be given by what? Circular plates, right? What's the area formula? Okay, so we have pi. The radius is 75 centimeters. 75.0, 10 to the minus 2 meters. Let's square that, so that's the area right there, pi r squared. And then the distance between the two plates, d, is 0.125 millimeters, so that's 10 to the minus 3 meters. Okay, so hopefully, if you believe me that this is a way we can write the units for epsilon naught, that this will come out in farads. So someone crunch those numbers for me. And while we're doing that, let's talk about the units real quick, okay? All right, so units for epsilon naught. So normally we think of this as coulombs squared divided by newtons times meters squared, if you remember when we originally encountered this quantity. But what I'm going to do is see what equivalents for the units we have, all right? So coulombs squared, I'm going to write that as coulombs times coulombs. And meters squared, I'm going to write that as meters times meters, like this. But one of those meters I'm going to group together with the newtons. See what I did? Okay. So what is a newton times a meter? What's an equivalent unit there? That's a joule, if you recall. A newton times a meter. So what we have is coulombs times coulombs divided by joules times meters. All right, so the next thing I'm going to do is I'm going to take one of these Coulomb factors and group it together with joules, okay? So here's how that's going to work. I'll take one Coulomb factor on top and just leave it there. But for the other one, I'm going to bring it down here and write this as joules per Coulomb, okay? And then we still have the meters right there. Now, does anyone remember this unit equivalency? What is a joule per Coulomb? That's what we call a volt. So coulombs divided by volts times meters is what we have right there. The last thing I'm going to do is take coulombs and volts and just sort of group those together on top like this. Coulombs per volts divided by meters. And what's a coulomb per volt? We just saw what that is. That's what we call a farad. So that's why for epsilon naught, I can think of the units as being farads per meter. It's really useful to see it that way because you can immediately see how the result of this comes out in farads. Okay? So that's where this came from. From now on, you can just remember that equivalency. We don't have to go through it again. Okay? Now, what is the capacitance? What do we get?
I got 1.25 times 10 to the 97.
Okay, yeah, 1.25, 10 to the minus 7 farads. So if we wanted to, we could write this as 0.125 microfarads, because micro is 10 to the minus 6. So typically, we'll use microfarads as our unit. Okay, so now we know the capacitance. The next thing we can do with that is use it to calculate how much charge accumulates on our capacitor when we apply a certain voltage to it. So for that, we're just going to use C equals Q divided by V, which gives us Q equals C times V. All right, so now let's take our capacitance of 1.251 times 10 to the minus 7 farads. But in this calculation, it's going to be useful to think of a farad in the following way. It's a coulomb per volt, right? And then in the first follow-up question, we were imagining the voltage is 12 volts. Okay? So can someone crunch those numbers for me? We're going to get some number of coulombs of charge appearing on the plates. What does that work out to?
Times 10 to the negative.
Yeah, 1.501, keep 3 sig figs, 10 to the minus 6 coulombs. So I could write that as 1.50 microcoulombs. Okay? And of course, if we were to instead use 12 volts, we would have 1.25, 10 to the minus 7 coulombs per volt as our capacitance, and then 48 volts as our voltage. So basically, if we increase the voltage by a factor of 4, we're also going to increase the charge that appears on the plates by a factor of 4. But what does that work out to? So you should be getting 6.01 10 to the minus 6 coulombs, which is 6.01 microcoulombs. Do we agree? Okay, so that's just a little bit of practice, not only using the formula for capacitance, but also using that to calculate charges. You're going to be doing this a lot over the next couple weeks. We good? Okay. So I'll put this over here if you want to see it later. So here's one for you. I want you to try this out. So let's suppose we have a parallel plate capacitor with 2 circular plates separated by a distance of 0.125 millimeters. So just like before, and we have empty space in between. So my question for you is, how big would we have to make the plates? What would the radius of the plates have to be if we wanted this to be a 1 farad capacitor? If we wanted the value of C to be 1 farad. So use this formula that we derived. Basically, you're going to calculate what the area of the plates is, given that C is 1 farad. And then based on that area, you're going to tell me the radius of the plates. Okay? So try it out, take a few minutes, then we'll go through it together. And if you're getting something that seems really large, that's actually probably correct. Okay, does anyone have an answer they want to throw out there?
2.08
Okay, so in what unit? It's like 2 kilometers, right? Again, that may seem like an absurd answer, but that's correct. So let's go through it. So here we have C for a parallel plate capacitor equals epsilon naught times A over D. And let's just go ahead and solve for the area. A is going to be CD over epsilon naught, right? So in this case, we're imagining that the capacitance is exactly 1 farad. I'm plugging in 1 farad for C. The distance between the plates is 0.125 millimeters. So that's 10 to the minus 3 meters right there. And then we divide by epsilon naught. Again, it's useful to write this as 8.85, 10 to the minus 12 farads per meter. That's the unit equivalency that we're using here. And hopefully you see that meters squared are the units we end up with. So can someone just crunch those numbers for me, see what we get?
Oh, 1.41 times 10 to the 7.
Yeah, that's a pretty big area. 1.412, 10 to the 7 square meters. And if we remember that this area is pi times r squared, well, we can calculate r. R squared is this area divided by pi. So then if we square root, we'll take the area we found, 1.412, 10 to the 7 meters squared, divide that by pi, and then take the square root. That's your radius. And this comes out to 2.12 10 to the 3 meters, or 2.12 kilometers. So obviously you're not going to build a capacitor with plates that are 2.12 kilometers in radius. So here's my question for you, right? Is 1 farad just unrealistic based on what we did here? Is it safe to say you can't build a 1 farad capacitor in the real world, or you couldn't put one in your pocket, let's say?
I think you could do it, it's just, maybe it's not practical.
Yeah, you could do it. There's just more to the design than we've been talking about here, which I'm going to get to in a second. So yeah, of course you could do this. 1 farad capacitors do exist. You can put it in your pocket, and you're going to see one in the lab next week, actually. Okay? So a few things. With just a parallel plate capacitor, it's not a very efficient use of space, if you think about it. You just have 2 giant sheets that run parallel to each other. What if instead of just having these 2 giant sheets, I took those sheets and I rolled them up into a tight space, like this? I could pack a lot more into a smaller volume that way, right? So that's what you see here. We have the 2 conducting sheets, and we separate them using some kind of insulating material so they don't touch each other. And then we just roll that whole thing up into a small space. So you can fit a lot of area this way in a relatively small space. That's going to help us, right? The other thing is, when we use this formula, we are always assuming that there's just vacuum in between the capacitor plates, which doesn't have to be the case either, right? Typically, we're going to have some kind of material there which will increase the capacitance, sometimes by many orders of magnitude, like hundreds of times, just by putting a certain type of material in between. And what that means is epsilon naught carries this value that we've been using, 8.85, 10 to the minus 12, for empty space, okay? If you're inside of some material, this takes on a larger value. So we'll see how that works in upcoming lectures. And then the last thing is, sometimes the sheets themselves can be covered with special materials that are highly porous, and basically those can help you increase the area too. So, for example, this is a material called activated carbon, and even if you just have 1 gram of this stuff, okay, because it's so porous, it has a surface area of about 1,000 square meters, okay? So all of these things can help you up the capacitance. So of course you can easily reach 1 farad if you just design it the right way. Okay? So any questions so far? So we've been talking about a parallel plate capacitor up until this point. Let me show you a different design. Okay, this is a cylindrical capacitor. And here's what it consists of. We have a conducting cylinder. Let's call the radius of that A. And then that cylinder is surrounded by a larger cylindrical shell of radius B. So you see we have the inner conductor, radius A, and then the outer conductor, radius B. Now both of these 2 conductors have the same length. Now, although the picture is kind of exaggerated, typically this length is going to be much larger than these 2 radii. Okay, so it's a very long set of conductors which share the same center. Okay? By the way, in a practical sense, a coaxial cable is basically this design. If you ever use a coaxial cable for your internet or TV connection, it's basically this thing right here. So we imagine hooking this up to a battery, we apply a voltage, and as we know, that means charge will accumulate on each conductor. So we're going to have positive Q accumulating on the inner conductor, negative Q on the outer conductor. So let me just remind you of what the steps are. First, we're going to calculate what the E field is between the 2 conductors. Then we'll use that to calculate the voltage between the conductors. And then finally, we'll use that to calculate the capacitance of this whole thing. Make sense? So those are the 3 steps we'll take. Let's do it now. By the way, what should I use if I'm trying to calculate the E field between the 2 conductors? Probably makes sense to use Gauss's law, right? This is a problem that's very convenient for Gauss's law. And let's just see how that goes. So we're going to calculate the E field inside the capacitor. And what type of symmetry are we dealing with here? Cylindrical symmetry. So I'm going to try my best to draw this picture. Here's the inner conductor. Okay. And then we have the outer conductor. Like this. And so remember, we have positive Q on the inside, negative Q on the outside. So generally speaking, which direction is my E field going?
Outward.
It's going outwards from this central line right here. So I'm just going to draw one of those E field lines. There are a whole bunch of them we could draw, but here's one of my outward facing E field lines. All right? So the next thing I'm going to show is my Gaussian surface. So I'm going to do that with a dashed line. Okay, the solid lines are the actual conductors in the problem. The dashed line is my Gaussian surface that I'm using just to analyze the situation. There we have it, something like this, right? So what does my area vector for this Gaussian surface look like? What direction is that pointing in? It's also pointing outwards. Remember, the way this works, if you have a closed surface, like the one I'm showing you, the area vector points outwards, and it's perpendicular to the surface. So there's my E vector, there's my dA. And again, I could show a whole lot more E field lines than this, but this is enough just to do the calculation. So we good on this? All right, so let's do this one. E dot dA integrated over the surface. Do you remember how this works out for cases of cylindrical symmetry? So if not, let's go through it again. E dot dA, let's do that real quick. So first of all, for the surface I drew, there's only going to be flux through this curved surface, not through the two end caps, remember? So I'm only thinking about the flux through the curved surface. So since we have a dot product, that's just E times dA, the magnitudes, times cosine of the angle between them, which is, what's the angle between my E and dA vectors?
0.
0. Next move I can make is to realize that over this entire surface I drew, that E has the same value. Because remember, E is only going to depend on how far away from the center we are. So at every single point along this surface, I'm the same distance from the center, so E should be the same value all across the surface. That's why I'm able to pull it out of the integral. It's a constant. And then that's multiplied by the integral of dA, which would just be the total area of that curved surface. So remember the trick for this one? Imagine rolling that up into, take a sheet of paper, imagine rolling that up into a cylinder, and then unfolding it, right? That's the area we're talking about. This is the length, this is the circumference, right? So it's just E times 2 pi r, that's the circumference, times L, that's the length. So remember where that came from, right? Okay, well, what's Q enclosed? And again, I'm assuming that I'm between the two cylinders. Just, yeah, positive Q, right? That's it. I'm only enclosing the charge that's on the inner conductor, but I'm not enclosing the charge that's on the outer conductor. So that's my Q enclosed. It's really that simple, okay? So therefore, check this out. In between the two conductors that's inside the capacitor, I'm going to apply Gauss's law, which says E dot dA integrated over my surface equals Q enclosed over epsilon naught. So what I get for E dot dA, we evaluated that integral. It's E times 2 pi RL. For Q enclosed, that's just Q. So here's what we get. E is equal to Q divided by 2 pi epsilon naught R times L. That's the strength of the E field inside of this capacitor, okay? Now notice it depends on our distance. So the E field is the strongest at the smallest radius, so over here, and it just gets weaker as we go up because it's 1 over R dependence, okay? Okay, next step. We're going to calculate delta V, that's potential difference. Or you could say voltage. These mean the same thing. Between the two conductors. So now we have a way of doing that because we can essentially just integrate from the inner conductor starting here to the outer conductor ending here. So we're going to start our integral here and we're going to end it here. Make sense? And remember, the integral I'm doing is minus E dot dl integrated over that path. That takes me from the starting point to the ending point. Make sense? Okay. So let's work it out. What can I say about my E field? I know this is the magnitude of it, right? It's Q divided by 2 pi epsilon naught RL. But if I want to fully express it as a vector, right, I would include the r hat unit vector, which just indicates that the E field is pointing outwards, right? Okay, what about my dl vector? That's just a little piece of the path that takes me from my starting point to my end point. So I'm going in the radial direction. A tiny bit of distance would be dr. And to include the direction, I'd have my r hat unit vector. So this is generally how it works if we're just moving radially outwards in this type of integral. Okay, now somebody tell me, what are the constants that I can pull out of this integral?
Q 2 pi epsilon and L.
Yeah, Q 2 pi epsilon naught L. R is not a constant, got to leave that in there. So I'll have dr divided by r. By the way, r hat dot r hat, that's 1. Okay, now what are my limits of integration for radius? So remember, we called the inner radius A, so that's where we'll start, and we called the outer radius B. That's just how we're naming things here. So this goes from A to B, correct? Okay? Now what do I get when I integrate 1 over R? Not quite. You're thinking derivatives, maybe. It's a natural log, yeah. So this is minus Q over 2 pi epsilon naught L, and then we get the natural log R as a result of this integral. And we take that from A to B. So here I have minus Q over 2 pi epsilon naught L. When I plug in my top limit, I get natural log B. When I plug in my bottom limit, I just get natural log A. And I subtract the 2 as usual, right? How can I condense this into something a little bit more concise? I can write this as natural log B divided by A. So I have minus Q over 2 pi epsilon naught L, natural log B divided by A. All right, cool. So we're almost done, actually. Because the last step is to apply the definition of capacitance. And if you recall, what's the definition of C? Q over V.
Can you put the paper up?
Yeah, sorry, Q over V. So basically, I'm going to take Q and divide by this expression for V that we found. Except, remember, I only care about absolute values here. Might as well just explicitly say, we don't care about the negative sign. That just means, we lose potential going from here to here. But that sign is not important for this definition, so we'll leave it off.
Is the delta not matter? Because it's delta V that we found, right? Is that
Yeah, so yeah, this is something to get used to also. In circuit language, we typically just say V when we're talking about a potential difference. So if I say like V for the battery is 3 volts, that's saying the difference across the battery is 3 volts. Yeah. Okay, so here we have the Q's canceling out. I hope you can see that. And then basically we're flipping this whole fraction right here. That gives me 2 pi epsilon naught L divided by natural log B over A. So that's for a cylindrical capacitor, what the capacitance would be equal to. Okay?
You said the Q cancels out.
Because I'm taking Q on top and then dividing by this expression. So when we do that, the Q's will cancel. Yeah. Anything else? All right.
Wait, what happened to the negative sign?
Okay. In the definition of capacitance,
Okay.
these are absolute values. Yeah. All right. So there's the result. Capacitance for this type of setup is given by C equals 2 pi epsilon naught L, natural log B over A. Okay? So let's go to the next topic, which is electrical energy storage. So the point that I want to get across here is that if we have a capacitor and it's storing some amount of charge, it's not only storing charge, it's storing energy. And that energy can be used at a later time. We can store some energy inside of a capacitor and make it available for later use. Like I said, this could be for like a camera flash unit, so we can release all that energy real quick to make the camera flash go off, or we could use it as a backup power source. There are a lot of different examples, but the point is there's some energy being stored when we charge up a capacitor. So what I want to show you is the formula, or actually a set of formulas, for what that energy actually is. Okay, so remember we have 3 different variables floating around. Let me just remind you. We have C, that's the capacitance of our device. And then we have Q, which is the magnitude of the charge on it, and then V, which is the voltage applied to it. So we can express things in different ways. Okay, so first I'm going to derive this formula for you. It says U, that's the energy stored in a capacitor, is a half times Q squared divided by C, where Q is how much charge is on it, and C is the capacitance. Okay, so we're first going to do this one, okay? But then, once we've derived that first one, we can simply use this definition of capacitance, which says C equals Q over V, to rewrite the formula in these 2 different ways. Okay, so it's really the same formula, but we're subbing out variables in these last 2 versions. Okay, so we're about to go through where that comes from. But the last thing to note about that before we go through a quick derivation is that, remember, we're talking about energy here, and technically there's a 0 point that we have to establish. The logical thing to do here is just to say, if there's no charge on the capacitor, there's no energy. That's our 0. So U is equal to 0 when Q is equal to 0. Okay? And then if we add some charge, then we have some energy. Make sense? All right, so let's go through the derivation. So what I want to show you is roughly what happens when we charge up a capacitor. So we're going to start with a capacitor. It's going to be a parallel plate capacitor in this picture, but this generalizes really to any type of capacitor. I'm going to start with uncharged plates. Okay, so if we have 2 uncharged plates, how can we start to charge them up? One way to do this is to take some amount of charge, let's call it dq, and then move it from one plate to the other. So if we think about it, if I lost charge dq from this plate, and we'll assume dq is positive, that means I've got a little bit of a negative charge now here, right? And then because I've moved charge dq to this plate, now I've got a little bit of positive charge here. So we can see that there's opposite charges building up as we do this. So just repeat the process over and over and over again until you've reached your final charge. What we're going to do is figure out, okay, how much energy was required to move all that charge over. That's what we want to find, okay? Okay, so start with uncharged plates, then move charge dq from one plate to the other. Until we reach our final charge of plus or minus capital Q on each plate. Okay, so capital Q is going to be what we end up with at the end. And then little q is just the little increments that we go over. Okay? All right, so to show you how this is going to go, remember that we have this formula which says delta U equals Q times delta V. So a change in potential energy when you move a charge across a potential difference is given by this formula, if you recall, okay? But here, what we're dealing with is infinitesimal amounts of energy. So I'll call this du. I'm going to write this in differential form. And we're dealing with infinitesimal amounts of charge, which I'm going to call dq, okay? Moving across whatever the potential difference between the plates is, okay? But I want to remind you that for a capacitor, okay, the potential difference between the plates is just Q divided by C, okay? We said Q is V times C, so we could say V is Q divided by C, okay? So this means the potential difference is constantly changing. At first, when the plates are not charged, there's no potential difference. But as we move more and more charge, as Q gets bigger, the potential difference keeps going up. So this is something we actually have to integrate. We can't just write down the answer yet, okay? All right, so let's go through that. What we have is du equals dq times q divided by c, where, just to be clear, dq is this little bit of charge that we move over, and q is the total amount that's accumulated so far. That's what that means, all right? If we integrate both sides, we're going to get the formula we're looking for. Okay, so on the left side of the equation, I'm just dealing with energy, and we start with 0 energy stored in the capacitor, and then we end up with some final value, which I'm just going to call U. So those are my limits on the left side, okay? On the right side, we're dealing with charge. We start with no charge on the plates, and remember, we're going to use big Q for our final charge that we end up with when this process is all finished. So the integral on the left side is actually very trivial, right? What happens when I take the integral of du from 0 to u? What does it give me?
U.
Just gives me u, right? So u equals, okay, let's work this guy out. I mean, basically, c is a constant, right? So what I'm integrating is just q. What do I get when I integrate q to the first power?
1/2 c squared.
So this, yeah, so I'm going to have a 1 over c, and then when I integrate, I'm going to get 1/2 q squared, and we're going to take that from 0, our initial charge, to big Q, our final charge, okay? So I have 1 over 2 times c, I'm just going to collect the 2 and the c together, q squared minus 0 squared. So that's where the first formula came from. It was q squared divided by 2c. So if I know how much charge is on the plates, and I know the capacitance, I can plug those right into this, and it tells me the amount of energy stored in the capacitor. Okay? So that's all well and good, but let's take it a little step further. What if I subbed in this formula? You've seen this one before. The amount of charge on a capacitor is equal to the capacitance multiplied by the voltage across its plates. So what if I just took that and put it into my energy formula? That would say U equals, on top now I have CV squared divided by 2C, right? So what's that going to give me? It's going to give me a half. I'll have C squared divided by C. That's just one factor of C on top. And then I'll have a V squared in addition to that. So I can also write this as a half CV squared. These are equivalent expressions, keep in mind. It's just a different way of writing the formula out, okay? Lastly, I could write this a different way. I could say, well, C is Q divided by V. And I could sub that into our original expression. And that would give me U equals Q squared divided by 2 times Q divided by V. So of course there's a 1/2 factor in this thing. Q squared divided by Q, that's just Q. And then this V comes to the top because we're dividing it twice. So I could also write this as a half QV. Again, these are all equivalent expressions. It really just depends on what information you're given as to what you want to use here, right? So if I know charge and I know capacitance, use the first formula. If I know capacitance and voltage, use the second formula. If I know charge and voltage, use the third formula, okay? Any questions on this? All right then. So that's where these formulas come from. Again, the first one is the real result. The others are just a result of making substitutions, okay? So with that in mind, let's do a quick question. Let's say we're dealing with a capacitor inside of a camera flash unit, and its capacitance is 150 microfarads. We charge it up to a potential difference of 200 volts. So a couple questions. How much energy is stored in the capacitor when we charge it up to 200 volts? And as a follow-up, let's say all of that energy that's stored in the capacitor is released in a very short time of 1 millisecond. If that's the case, what is the power output of this camera flash? So first you're calculating the energy, then you're calculating a power. Remember how to calculate power? That's the energy released divided by the time it takes to release it. Yeah. So try this out, see what you get, and we'll go through it. joules, and that corresponds to 3,000 watts. Yeah. Pretty straightforward. Okay, I see some people are getting this. It's good. Let's go through it together. So, what we know is the capacitance and the voltage. So it stands to reason the simplest way to get the energy stored would be to say 1/2 CV squared, right? So let's do that. We have a half. Our capacitance is 150 microfarads, so that's 10 to the minus 6 farads. And then our voltage is 200 volts. And we have to square that, right? So what does that come out to?
0.03?
This one?
0.03, does it?
I just got 3.
Yeah, it should just be 3. Remember, this is 150 right here.
Oh, okay.
If you put in 1.5, you'd get that, but it's just 3, and the units come out in joules, okay? So, all right, so if we're releasing 3 joules of energy, and it takes us 1 millisecond to do so, the power would be the energy released per unit time, which would be 3 joules, and then the time, I can write this as 1 millisecond, or 1 times 10 to the minus 3 seconds. All right, so this is 3 times 10 to the 3 joules per second. What's the equivalent unit right here for a joule per second?
Watt.
That's a watt. So 3,000 watts, but only for a very brief amount of time. Okay? Any questions?
How does the farads times volts squared come out to joules?
Yeah, we can go through that. It's a little bit, takes a minute, but here, farads times volts squared is what we have, right? So, do you remember what the equivalent unit for a farad is? Yeah, it's a coulomb per volt, and then volts squared, right? So that's a coulomb times a volt, isn't it? What's a volt equal to? A volt is a joule per coulomb. So we have joules. So yeah, I'm not always going to have time to show these unit equivalencies, especially as we keep going. The units are just going to pile up. We're going to have, electrical resistance, current, magnetic fields, right? A good rule of thumb is if you plug the numbers in with SI units, what you'll get out has SI units. Okay, so sometimes we'll just show the unit equivalencies, but other times we'll just have to skip through that because it takes a while to do. Okay? I guess in this case it wasn't so bad. All right, so that brings us to something called energy density. So the idea here is pretty simple, right? If we have a capacitor and it stores some energy, the capacitor itself has some kind of finite volume. And if we just take the energy stored divided by the volume, that's an energy density. Okay? Just like mass density is mass over volume, charge density is charge over volume, energy density is energy over volume. That's the idea. So we're going to derive a formula for energy density, and we're going to start off assuming that we have a parallel plate capacitor and we're concerned with the energy stored inside of it. However, the result we get is actually completely general. It doesn't even have to just apply to a parallel capacitor, parallel plate capacitor. It can really apply to any situation. So let's see the idea here. So we have a parallel plate capacitor where one plate is charged to positive Q, the other is negative Q. And we already worked out that the potential difference across the plates is just the magnitude of the E field times D. And again, here, I'm just using an absolute value. Don't worry about the sign, okay? We also saw that the capacitance is epsilon naught times A divided by D. So these are things we worked out in previous derivations, okay? So why don't we take those expressions and plug them into the formula for potential energy? Because after all, U is equal to 1/2 times CV squared. Take this expression for C, this expression for V, and place them right inside. Okay? So here's the direct substitution. We have 1/2. C is epsilon naught times A divided by D. And V is the electric field times D. And we're squaring that whole thing, okay? So we can simplify this just a little bit. I have D squared on the top from my voltage expression. And then I have 1 factor of D on the bottom from my capacitance expression. So overall, that's just a factor of D on top, right? And then the rest is this. I have 1/2. That comes from the very beginning of the expression. I have an epsilon naught factor, came from the capacitance expression. And then I'm squaring the E field. That came from over here. And then I just have the area of the plates times the distance between them. Okay? Now, can someone tell me, like, if I take the area of these plates times the distance between them, what does that give me?
Volume.
That's the volume in between the plates. Do you see that? The area times the distance is the volume in between the plates. It's important to recognize that. So the volume of the space between the capacitor plates is A times D, which is what you see at the end here. Okay? So if we were interested in dividing out the volume, right, that would just be dividing out this piece. So what would I be left with for energy density? What would be my formula for energy density if I did that? Yeah, I would just get this part right here, because I would divide out this part, which is the volume. I would get 1/2 times epsilon naught times E squared. This right here is the energy density. Does that make sense? So here, energy density, electric energy density in particular, is given by lowercase u. Okay, so uppercase U is just energy, lowercase u is energy density. And it's the energy stored per unit volume, not just in a capacitor, by the way, but in any electric field. So we'll see how this generalizes. And we can write it this way in differential form. Lowercase u is du dV, energy per unit volume. But like I said, if we take this formula up here for the energy stored in a capacitor, and we divide out the volume part, we're just left with this part. And that gives us 1/2 epsilon naught times E squared. Okay? So again, I want to emphasize this. Although we looked at a very special case, a parallel plate capacitor, to get to this result, the result itself is perfectly general. So whenever you have an electric field, there's an energy density, and we can calculate it using this formula. Okay? So any questions on how we got here? Hopefully it's pretty straightforward. Okay, so if there are no questions, we'll keep it moving. I want to give you a little practice using the formula. So you may remember from the last lecture that there's this idea of electrical breakdown, where if the electric field strength in a material is large enough, that material can start to act like a conductor. So for example, if we're talking about the air, if the electric field gets as high as 3 × 10⁶ newtons per coulomb, that's when electrical breakdown will begin to occur. And you'll get this sort of situation where you'll discharge a charged object through the air. So the question here is, what is the energy density, lowercase u, in the air when this happens? All you need to know is the value of the E field. So this is the formula we derived. Just do a straight plug and chug, see what you get. Okay?
What are the units for that density?
Okay, so good question. If it's energy divided by volume, What's our energy unit going to be? Joules. What would our volume unit be? Joules per meter cubed is an energy density. So yeah, the calculation itself is pretty straightforward. So once you've done that, try to see that you can convince yourself the units come out as joules per cubic meter. All right, so what are we getting for this, everybody? Yeah, about 40. I would agree. Let's go through this, and in particular, let's go through the unit analysis, okay? So energy density, as we just found, lowercase u, is given by 1/2 times epsilon naught times the electric field strength squared. So to put in the numbers, we have 1/2. Epsilon naught is 8.85, 10 to the minus 12. I showed you we can think of this as a farad per meter, but I'm going to actually just use the standard unit of coulombs squared divided by newtons times meters squared. And then we'll take our E field, which has units of newtons per coulomb, and plug in 3 times 10 to the 6 and square it. So you're right, we get 40 as our numerical value. But let's see what units come along for the ride. It looks to me like we have coulombs squared divided by newtons times meters squared from this. And then from squaring the E field, we get newtons squared divided by coulombs squared. We agree? So coulombs goes away entirely. Okay? And then I have newtons squared on top, and then just newtons on the bottom. So that's just one factor of newtons on top, right? And then meters squared still on the bottom. So what I'm going to do with that is I'm going to multiply meters on both the top and the bottom. I'm allowed to do that because I'm not changing the value, right? So if we do that, we'll see that on the top I have newtons times meters now, and on the bottom now I have meters cubed. But remember, what's a newton times a meter?
A joule.
That's a joule. So that's how we get joules per cubic meter as our unit. That's where that comes from. Okay? Any questions? All right, let's keep it moving. So what I'm going to explain here is a basic process that we can use to calculate the energy stored in some electric field. Okay? And then we'll look at one example of this, and then that's probably all the time we have. So first point, whenever we have an electric field, we have energy stored in the space that the E field is actually filling out. Okay? So again, that's not just true for a capacitor, it's true for any electric field we might have. If we look at the formula for electrical energy density, it's proportional to E squared. So that means there's more energy packed into a smaller space the larger the E field is. Okay, the E field is smaller, your energy density is also smaller. So if we have some kind of electric field, here's a strategy we can take to find the total energy stored all across that field. Okay? So first, we can use either Gauss's law or Coulomb's law, whatever happens to be more convenient for the situation, to calculate what the E field actually is. Right? So first we want to know what the E field actually is. Then, once we know what the E field is, we can plug it into this formula for electrical energy density. Just plugging in the formula for E tells us the energy per unit volume in the space surrounding our E field, right? And then finally, if we take energy density and we integrate it over a volume, then we'll get the total energy stored in whatever space we're talking about, okay? So find the E field, find an expression for the energy density, and then integrate that thing over volume, and that gives you the total energy. Does that make sense as 3 steps to take? So let's see an example of this. All right, here we have a non-conducting sphere, radius big R, total charge Q, and it's uniformly distributed over the volume. This should look familiar, we've seen this before. But the question here is, what is the total energy stored in the electric field? So let me kind of give you the sense of how this is going to work. Remember, the E field kind of has a different expression depending on whether we're inside or outside of the sphere, right? Remember that from Gauss's law? So basically, I'm going to calculate the total energy stored inside the sphere, in this electric field, as well as outside the sphere. And for outside the sphere, I'm literally talking about all the way out to infinity, all of space outside of the sphere. So we'll do both of those, we'll add them together, and of course that's the total energy throughout all of space, okay? All right, so what kind of symmetry are we dealing with here? Should be pretty obvious, right? Spherical symmetry. So we're going to find the E field, which is spherically symmetric. Okay, for that we're going to use Gauss's law. So I'm going to draw the actual non-conducting sphere right here. Then I'm going to draw a Gaussian surface, which I'll show with the dashed line. And then I'll show that my E field is spherically symmetric. So it's just going out radially in all directions. I'll just show one of the representative E field lines just for visual purposes, but it's going out in all directions. Okay, my dA vector also points radially out because it's going away from the surface of this, this sphere that I drew, right? So that means, let's work it out. The integral of E dot dA over this entire thing. Does anyone remember what this works out to? Yeah, it works out to E times 4 pi r squared. Okay, let's just go through it real quick. The reason for that is we have a dot product, which is E times dA, the magnitudes, times cosine of 0, because they're pointing in the same direction. Then we get to pull out the E field, because over the surface we drew, it's totally uniform. It only depends on distance from the center. So over this sphere, it has the same value everywhere, which is why we get to pull it out. And then we just have integral dA. So that's the total surface area of the sphere we drew here with the dashed line, which, like we said, is 4 pi little r squared. So just to be clear, little r is the radius of our Gaussian surface, whereas big R is the radius of the actual non-conducting sphere. Okay? Now let's think Q enclosed real quick. So for the time being, let's assume that little r is less than big R, which means we're inside. How can I think about the charge I'm enclosing? Well, the charge is uniformly spread out all over the non-conducting sphere, right? So that means, okay, because the charge is uniformly distributed, that means that the charge density rho is just a constant. The charge per unit volume is the same everywhere. So Q over V is the same everywhere, is another way of saying that. So I could take the charge I'm enclosing, Q enclosed, divided by the volume I'm enclosing. And that should be the same as if I took the total charge and divided by the total volume. So remember how we set this up? Okay, so Q enclosed, therefore, is the total charge times the volume I'm enclosing with this surface divided by the total volume. Remember this? Q total, in this problem, we're just calling that Q. And then, what's the volume that I want to use here? What's the formula for a spherical volume? Yeah, so it's 4/3 pi r cubed, because we're talking about a volume. But for the volume I'm enclosing, I'm going to use little r. And for the, I said cubed, so I should write cubed. There we go. And then for the other one, we're going to use big R for the total volume. Does that make sense? So this can be written in a much simpler way as Q. We have little r cubed divided by big R cubed because the 4/3 pi factors drop out. So that means if we apply Gauss's law, E dot dA equals Q enclosed over epsilon naught, we will get E times 4 pi little r squared, that's the E dot dA portion, equals this Q enclosed divided by epsilon naught. So I'll just write 1 over epsilon naught to make sure we don't forget it. And then we have Q times little r cubed over big R cubed. Okay? Which means E is equal to, let's write it out. I have Q divided by 4 pi epsilon naught big R to the 3rd power. And then what am I left with? How many factors of little r? Just 1. So, of course, this is the E field inside of this charge distribution. So we found the E field on the inside. We also want to do it on the outside. Now let's assume that little r is bigger than big R. So imagine a surface that's on the outside. Okay? How much charge am I enclosing in that case?
It's Q, right?
Yeah, I'm enclosing the total charge on the sphere if I'm outside of it. Make sense? So it's just Q. So this is much easier to work out. We have E dot dA equals Q enclosed over epsilon naught applied to this surface where we're outside of the sphere. That gives me E times 4 pi little r squared, that's the same as before, equaling Q over epsilon naught.
You with the paper?
Yep. So we're good up to here. So just solve for E. That's Q over 4 pi epsilon naught little r squared. So again, this one applies to the inside, this one applies to the outside. Does that make sense? So we have the E field both inside and outside. Okay, the next step, if you remember, is to calculate the energy density. So find U, which is the energy density. And we're going to have two different expressions for this, right? One of them is going to apply to the inside, the other is going to apply to the outside. So let's start with the inside expression. This is going to be 1/2 times epsilon naught times the magnitude of the E field squared. If we do this for the inside expression, which is this one right here, I'm going to have 1/2 epsilon naught, and then E, it's going to be this whole thing, Q over 4 pi epsilon naught big R cubed times little r, but I'm going to square the whole thing, okay? So let's just keep track of what we have here. It's going to get a little messy, but we can do it. So on the bottom, I have 4 squared. What's that? 16. And then I have a half also, so that's 32 on the bottom. Do we agree? Okay, on the top, I have a Q squared from this, and an R squared from this. Little r squared, I should say. Okay, on the bottom, I have pi squared. That doesn't cancel with anything, so it's just pi squared. I also have an epsilon naught squared from this, but I have one factor of epsilon naught on top already. So there's just one factor of that on the bottom. And then finally, I have a big R to the third power, and I'm squaring that. So what's my power overall when I square it? 6 power. So that's my energy density on the inside, which means little r is less than big R. Okay, just do the same exact thing for the outside. So in this case, remember, this is our E field on the outside. So I'm just going to plug that directly in, which is Q over 4 pi epsilon naught times R squared. That's the E field. We're squaring the E field, remember. So same basic idea. Let's just kind of collect all the factors, see what we have. I have Q squared on the top. I still have 32 pi squared times epsilon naught on the bottom. That's the same as before, right? But now I have little r squared, and that gets squared again, so that's the 4th power overall. Okay? So we agree? This is on the outside. So it kind of makes sense on the inside that our energy density is growing with radius, because we keep enclosing more charge as we go out. But on the outside, it's getting smaller with radius. That's what we see here. Okay? So we good on this? All right, so we're going to take the last step, which is, this is the energy density. If we integrate this thing over volume, that gives us the total energy stored within that volume. So we have to be a little careful about how exactly we do this, but the basic idea is we'll have 2 separate integrals to evaluate, one for the inside, one for the outside. Okay? So the last step is we're going to integrate to find the total energy. All right, so here's how you should think about this one. Energy density, that's lowercase u, is du dV, energy per unit volume. And I have to write this in differential form because it's not just a constant, right? As we can see from what we found earlier, it depends on your radius. It's not just a constant value. So that means du, some tiny amount of energy stored, would be little u, the energy density, times dV, some tiny piece of volume, right? Does anyone know, by the way, how to write dV, some tiny element of a spherical volume? We did go over this before, but I want to see if you remember.
dr times 4 pi r squared.
Yeah, 4 pi r squared dr. That's how we write the volume element, okay? Do you want to go over how this works again?
Oh,
All right.
just derive the volume, right?
Yeah, just you write the volume out, you take a derivative to get this, right? Pretty straightforward, okay? Okay, so that means if I wanted to get the total energy, I would be integrating over du, which means I'd be integrating over little u times dV. So I'd be taking the energy densities that we found earlier times this volume element and integrating that whole thing, okay? All right, so we have to do this both for the inside and the outside. Let's start with the inside. Okay, so our inside expression, I'll write this as un. is the integral of energy density times dV. Remember, this is our energy density expression right here. I'm just going to pop that in. And then this is our dV expression. I'm going to pop that in as well. Okay? Okay, so for our energy density, we got Q squared times little r squared over 32 pi squared epsilon naught big R to the 6th power. And then for dV, we have 4 pi little r squared dr. Okay, I know there's a lot of factors floating around, but hopefully you see why I'm plugging these two things in. Can we simplify that? So what's 4 over 32? That's, yeah, just 1 over 8. By the way, Q is a constant, so I can pull out Q squared. On the bottom, I have a factor of 8. Here I have a factor of pi squared on the bottom, so just overall factor of pi on the bottom. And then epsilon naught also appears on the bottom. So you see how I can kind of collect the constants like this, just pull them all out? What am I left with after I've done that? Oh, actually, I have a big R to the 6th too. I can do that as well, right? Okay, so those are all the constants I can pull out. What am I left with once I've done that? How many factors of little r?
4.
Little r to the 4th power dr. What should I be setting as my limits of integration? Remember, we're just trying to figure out how much energy is stored inside the sphere.
So 0 to R.
0 to big R, if I'm just including the interior of the sphere. Yeah, that's correct. Okay, R to the 4th power, what does that give us when we integrate?
1 over 5 R to the power 5.
1/5 R to the power of 5 is the result of that integral. And then we have these constants, same as before. So look, we know that when we plug in the bottom limit, we just get 0, right? We plug in the top limit, we get 1/5 big R to the 5th power, right? So I'll just write that out real quick so we know. So same constants out front. And then 1/5 big R to the 5th power minus 0. So overall, that's Q squared. On the bottom, what's my overall fraction? It's 8 times 5 on the bottom. 40? 40 pi epsilon naught
Big R.
big R, right? Because that big R to the 5th over big R to the 6th. That's the energy stored on the inside. So we're almost done. Let's just do it for the outside. So for the outside, where we're at a radius bigger than big R, my energy is given by the integral of my energy density, which is this thing right here we found earlier, and then the same volume element that we wrote down earlier. So here, let's write it all together. Energy density is Q squared over 32 pi squared epsilon naught little r to the 4th power. And then I have 4 pi r squared dr, like this. Okay, so what are we left with when we collect our constants? We have Q squared to pull out. 4 over 32 is 8. Pi over pi squared is 1 over pi, like this. And then we have epsilon naught. And then we don't have any big R factors, so nothing can be pulled out in that respect. So then overall little r, what do we have as our overall factor? Yeah, so dr over r squared. What do I want to set my limits to here? Yeah, big R, so that's just barely outside of the sphere. And then just take it as far as you want it to go, infinity. So that covers all of space. okay? Because we've included all of the inside and all of the outside. And what do I get when I do this integral right here? Yeah, this becomes negative 1 over r. Q squared over 8 pi epsilon naught minus 1 over little r, going from big R to infinity. Let's plug in the limits. I have minus q squared, taking the negative sign and just putting it out here, over 8 pi epsilon naught. And then I have 1 over infinity minus 1 over big R. And 1 over infinity goes to 0. So I just have two negative signs canceling. And I have q squared over 8 pi epsilon naught big R. So a very similar kind of expression, except the overall factor is 1 over 8 as opposed to 1 over 40. But other than that, it's the same expression. And the last step we take is to find the total. That's just all the energy on the inside plus all the energy on the outside added together. Which is, so notice with these two expressions, we have q squared over pi epsilon naught big R. It's just that in the first case, we have 1 over 40 coming along with that. And in the second case, we have 1 over 8. So I'm not going to bore you with fractions, but you can reduce that to 3 over 20. If you add those together, it's 3 over 20. So we have 3q squared over 20 pi epsilon naught r. That's the answer. Okay. So any questions on how we did this? I know it's kind of a long process, but hopefully you're seeing what the steps are. And of course, it's easy to make a mistake somewhere along the way. This is a long problem. I'm surprised I didn't screw it up, frankly. So we're going to do another example of this next time we meet for lecture. That's all for today. Remember, if you're in the Wednesday lab, we are meeting today for lab, but if you're in the Friday lab, we're not meeting this week, okay?